Good evening. My name is Kinion Fowler. I am a junior in the Randall Research Scholars Program studying aerospace engineering. My research project is entitled Dynamic Stress Analysis through Tailor Impact Testing. It was conducted under Dr. Mark Barkey in the Impact and Penetration Mechanics laboratory here on campus. So in this presentation, I'll give you a brief overview of what a Tailor test is and why it's important. Then I'll discuss our current project's goals. Then I'll walk you through a Tailor test and the procedures that we go through. And finally, I'll talk about our next steps. Tailor tests were first put forward by Sir Geoffrey Taylor in 1948. Put simply, it's a test where a cylindrical sample is fired out of a tube, and then it impacts a rigid, flat plate. On the impact, the sample will deform, and we can measure that deformation to determine the yield strength of the material. What you see on screen is an excerpt from Dr. Taylor's original paper. It's an image depicting the different ways he expected the samples to deform. Determining the yield strength of these materials is important because that's obviously important for impact testing like we're doing, but it's also applicable to anything that's undergoing shocks or impacts. So, and everything from an aircraft's wings to a spacecraft's landing gear. Our lab has previously done work under Dr. Stanley Jones to develop a one-dimensional method of analysis for Tailor impact tests. This greatly simplifies the analysis process by assuming that radially the sample deforms uniformly and it only changes along its length. That was several years ago, and we're currently in the process of updating our lab to do more testing. A typical sample after a Tailor impact test looks something like this. On the right is a sample of rolled copper that has just undergone a Tailor impact test. The middle is a graphic that depicts the two different methods of deformation. So on the end that's closer to the plate, the target plate, it undergoes plastic deformation, and farther away, it undergoes elastic deformation. Elastic deformation is where a sample deforms but returns to its original shape, whereas plastic deformation is permanent deformation that does not return to its original shape. The yield strength of a material is the amount of stress it can take before going from elastic deformation to plastic deformation, and since our samples have that transition point, we're able to calculate the yield strength from that. So our current project has four main goals. That's to update our existing laboratory. Once we've done that, we're validating our test setup by firing projectiles without impacting them. That's just to test that our test stand works and that we're measuring velocity data correctly. Then we're going to test with solid samples, perform Tailor impact tests. We're going to be using copper, aluminum, and steel samples to start with, and that's just to be able to compare to known values for their yield strength, again, to make sure we're getting accurate data. Once that's done, we plan to test with additively manufactured samples. What you see on screen is an additive friction stir deposition printer. That's printing metal, but as you can see, it has distinct layers to it, and we expect that that will dramatically impact the deformation and the yield strength of the materials. So for each test, we first have to prepare our targets and our projectiles. The target has to be lapped to a smooth finish. That's to ensure that when the projectile impacts it, it deforms uniformly and does not deflect off in one direction or another. We also have our projectiles that we take from a normal cartridge, such as 17 caliber, 223, or 308. The model you see is of a 17 Remington cartridge. We remove the bullet from it, adjust the powder load so that the velocity is what we need it to be, and then replace it with our milled down samples, cylindrical samples. Then we perform our actual testing where we fire them and measure their velocity. We measure the deformation after impact using a laser micrometer, and finally we're able to use those measurements we took to calculate the yield strength of the material. This is a model of our test stand. I'll be showing you it from right to left because that's the direction of travel that the projectiles take during a test. So first we have our breech on the right. This is what contains the explosive force from the gunpowder. We are able to screw it and unscrew it, and that's how we load in our samples. It also has a solenoid on one end of it, and that's able to be triggered remotely. Our actual test stand is in a separate room surrounded by ballistic padding and cinder blocks, and during tests we are always in a separate room for safety reasons. Next you have our barrel, that's where the expanding gases actually accelerate the projectile. It has an adjustable height so that we can control exactly where on the target we're impacting afterwards, and it can be interchanged with different barrels for different cartridges. Again, the three main types we use are 17, 223, and 308. This tube is also not rifled like most gun barrels would be. That's because the added spin of the projectile could cause it to deform non-uniformly. Next, we have our lasers. This is what we use to measure the velocity of the projectile. As the projectile crosses through the lasers, we have them synced to an oscilloscope, so we're able to measure the time that the beam is broken. We know both the length of the projectile and the distance between the two lasers, so we are able to calculate the velocity in two different ways. Excuse me. Finally, we have our target. This was polished hardened steel alloy, as I talked about. It's attached to a rigid, heavy piece of metal to add rigidity to it. And it can also be swapped out with a catch bin that can be filled with sand or wood chips for testing that it does not involve impacts. Here are some images of our test stand. On the left, you'll see the polished finish on the target, and on the right, you'll notice that the projectile has an obturator between it and the cartridge that we're using. That obturator is what helps attach the projectile to the cartridge, and also as the gases expand down the tube, it helps push the projectile down the tube. So our next steps would be to validate our test stand improvements once we finish making them. Again, that involves testing without doing an impact. This would be a cartridge that's been unmodified, so we know the target velocity, and we're able to compare that to what we measure. Then we're going to test with the solid samples and measure their dynamic stress that they experience to calculate their yield strength. Once we complete that, we're able to test with additively manufactured samples of the same material. Eventually, we would also like to do comparison with finite element analysis like you see on screen to see how that compares to our empirical results from our testing. So in summary, Taylor tests are a very useful method to calculate the dynamic stress of materials, which is useful to determine how they will deform. We are currently rebuilding our test stand, and we plan to test steel, copper, and aluminum specimens early next semester with the goal of testing 3D printed materials soon in the future. Thank you for listening to my presentation. Are there any questions?
Hello, could you please go into a little more detail on how the velocity of the projectile is measured and the impact it has on your study?
Of course. So as I mentioned, we have lasers that are mounted overhead on our test stand. These project into optical sensors below the test stand, and as the projectile fires, it will break each beam independently, and we're able to record the time on an oscilloscope. By recording that time and knowing the length of the projectile and the distance between the two lasers, we're able to calculate the time. This is important to understand the kinetic energy that the projectile has before it impacts the plate, which is used in our deformation calculations.
So what kind of velocity do you target, and why?
So the target velocity is going to depend on the sample we're testing. As I showed in the diagram previously, we need to have a section where it goes from plastic deformation to elastic deformation. This is, if it deforms completely elastically, the test is not useful, and if it deforms completely plastically, the test is not useful. So we need to have a velocity that's in between. Typically, this is in the range of 100 to 400 feet per second, but it depends on the material.
Why is it important that the samples don't all impact the same location on the target repeatedly?
So even though the target is a hardened steel alloy, each impact is going to cause small dents in it, and over time that would make the surface uneven. So we're aiming not to impact the same location twice on the target. This means that the unevenness of the target is important because it would cause the samples to deform non-uniformly or in ways we can't predict.